in Hubble. And they pretty well vowed that they would be involved in the next big project. And the next big project came along in the early 1990s. That was to succeed the Hubble Space Telescope. Okay, very good. I'll pick successor to Hubble, which was called at that time the Next Generation Space Telescope, and the discussions were being held. Okay, good. So in the early 1990s, NASA and the US community really looked at what they, back in the early 1990s, when NASA and the United States were contemplating the next, let's try one more time, perhaps. In the early 1990s, the US were developing their next generation, what they call the. For those of you who are maybe listening in, sorry for the delay. We're just trying to see if there's some technical issue that we can resolve here, rather than it going on and off very too frequently. So, just stand by.
Sorry, everyone, we've identified the problem. We're going to stop the broadcast for a second and correct it. We will be back within 10 seconds.
Good, I think we are back in the air. Let's keep our fingers crossed. So in the early 1990s, the NASA and the United
using feed loop because specifically of problems like this.
Okay. How was the press conference this morning? Was it well attended?
There were fewer journalists than I expected, but it went well overall, and we were on social media as well. Okay, good. I'll pick it up again. We'll see if we can continue. So I'm going to continue beyond the early 1990s. Canada at that point in time was invited to participate in a panel which lasted a couple of years, called HST, Hubble Space Telescope and Beyond. And one of our prominent astronomers from the University of Toronto named Simon Lilly was a participant in that, and was feeding, of course, the information back and forwards. And it was clear that the United States were interested in an international partnership. They were also at the same time talking to the European Space Agency as well as the Canadian Space Agency about possibilities here. So we spring forward to 1997. After initial studies had been done about what this telescope was going to look like and what it was going to study. Erick has already told you that it was, at that point in time, a relatively modest sum of money. In fact, initially it was thought to be a $500 million US telescope, not the 10 billions that we have now. And Canada had a formal invitation from NASA in 1997 and became a major focus of its decadal astronomy plan, Canadian decadal astronomy plan for the years 2000 to 2010. At that point in time, Canada, the CSA and the Canadian Space Program was going through an interesting time as well, in that it was developing what is now called the Long-Term Space Plan 3. Up until that time, we had been funded, the Space Agency had been funded for 5-year increments, and we were going for a change in that direction, and put a major application into the government, not only to have continuous funding, ongoing funding rather than 5-year funding, but also to fund specific projects at that time. And the NGST, Next Generation Space Telescope, became one of those asks. Fortunately, the government at that time did give us the approval to go ahead with the Long-Term Space Plan 3. And along with the NGST, which in 2002 was renamed into the James Webb Space Telescope. And a lot of credit for that goes to Mac Evans, who was the president of the Canadian Space Agency at that time. Mac was really strongly supportive and influential in getting not only the ongoing funding for the CSA, which is, of course, had ever since, but also for the amount that we were going to contribute to the James Webb Space Telescope, which at that time was to be roughly a US $50 million contribution. This was to be allocated for both a hardware contribution and some science instrument. And interestingly enough, there were several initial studies performed by Canadian industry on potential hardware contributions, including a communications package. We're very strong, of course, in communications, telecommunications in space, and a possible mechanical structure with an emphasis on vibrational control. In the end, neither of those really made it through the review, and eventually in 2001, Canada was asked to contribute a fine guidance sensor, which of course is our major contribution to this telescope, and quite remarkable. Even now, it's a remarkable ask that NASA and the Americans were willing to ask a foreign partner, to provide really a core piece. If the fine guidance system does not work, the telescope basically fails. All the rest of the stuff that's in there, all the instruments, they just don't do anything. So it is a major contribution, and a very special contribution. But it was based on some history we had, because again, the Canadian astronomical community had negotiated, and the CSA had been able to fund a fine guidance sensor on the Far Ultraviolet Space Explorer telescope, which was launched in 1999. So we showed to NASA that we could do this. We could actually provide the heart, the core of a technical piece to a very large project. The team also was working, and the science team was working on an instrument. I won't go into that in many detail because I'm sure Neil will talk to us about that. Initially, we thought we would try and provide a multi-object spectrograph, but then ESA was chosen to provide that instrument. I don't think we could have afforded to actually put that instrument together. But then we looked at, so the Canadian science team looked at a tunable filter imager, which was initially going to be part of one of the American instruments called NearCam. And then that became a separate instrument that was integrated into the fine guidance unit. And that was then changed in 2011 when there was some technical difficulties associated with the cryogenic operation of the instrument, and it then became the NEARIS. Again, I'm sure Neil will mention that, and I will now really pass on to Neil. But before I go, I would like to make a little statement here because I think it's important for viewers to appreciate. This remarkable project for Canada was, of course, made possible by the outstanding leadership, foresight, and excellence of the Canadian astronomical community, the skillful and masterful contribution of the industrial team, which Neil represents, working together with the scientists, by the openness and leadership of the Canadian Space Agency to strongly support space science and actively engage in international partnerships, as well as the excellence of the CSA project management team, which of course Erick has contributed greatly to. And most importantly, I think, by the confidence developed over 2 or more decades within NASA in our ability to contribute significant hardware of a critical nature to a US flagship space science mission. This confidence is not easily won, and over the past half decade, this has been stretched by Canada's, I believe, lack of ambition to support our outstanding space scientists through international collaborations outside of our space exploration program. Of course, our space exploration program has tremendous international collaboration, but besides that, in the other branches of space science, I think there is unfortunately a bit of a lack of opportunity here. And I really do personally hope that the success of JWST will reinvigorate the Canadian Space Agency's support for its space science program by enhancing its world-class space science community through new opportunities to work with our international partners on cutting-edge
projects. We've shown we can do it. We just need a little bit more, I think, contribution and support from the government, which I hope the James Webb Space Telescope will enable. So I'll pass over now to Neil. Thank you very much.
Sorry to stop you here, Neil. We don't seem to have any sound for you. Are you muted?
Mike?
Yep, Mike. I have two mute buttons. I apologize. I only hit one of them. Yes, so I prepared a few slides that we can go through just to introduce the hardware, since there's a lot of pictures of hardware, as you can imagine. So I'll go into presentation mode right now, and hopefully that comes through okay. If it behaves. There we go.
Everything looks great.
Okay, so yes, so we have the just a quick overview of the guider and nearest instruments and some of the test program that we went through. And to introduce the hardware, I really have to talk about the architecture of the observatory. So here's a cartoon view, I guess, of the overall observatory, and you can see the location. Well, next slide will show you in more detail, but just to orient you to the major observatory items, we have the primary mirror here, of course, and it's actually a 3-mirror telescope. There's a corrective mirror in the back here, the tertiary mirror, and then light path comes off the secondary, of primary, secondary, tertiary in the back, to a fine steering mirror out here on the aft optical system. And the fine steering mirror, of course, is what's of interest for the guider, because that steering mirror is moved by signals, the process centroids that we provide to the spacecraft. So all the cold instruments are in the back here in the integrated science instrument module, and of course that's the 4 mentioned, and FGS is there. And then the spacecraft is below the sun shield, which is shown transparently. And the next slide will show you the location of the FGS hardware. So within the ISOM, the 3 instruments are here, and buried right in the center is the FGS nearest optical assembly. Then there's a transition harness coming out to actually a set of warm electronics that have these louver radiators, which allow the electronics to run warm while being on the other side of the sun shield. So one of these boxes is I think that one is the FGS nearest, and then not to forget, of course, the software that we had to develop to control the guider and the nearest instrument, and that is in the ISOM command and data handling unit, which actually sits on the spacecraft side of the observatory. So those are the component locations. And then just to go over the purpose, sometimes use some analogies, but basically the FGS is to keep the observatory pointed at its target with exquisite accuracy to enable the sharpest possible science images for all the science instruments. So it can sense the, I apologize. So it can sense the drift or vibration of the telescope to very fine accuracy, and it basically measures that position of the guide star 16 times per second as the telescope can drift within its attitude control envelope. And that, as I mentioned, sends that signal to the fine steering mirror inside the observatory. So FGS will be used in fine guiding mode for almost all of the science images taken by Webb. There are special cases where we will track guide stars as the telescope moves, and that's done so that we can observe solar system objects, the planets, asteroids, comets. So if you want an analogy as to how fine it can point the telescope, is thickness of a human hair from about 1 kilometer away, or seeing somebody blink in Toronto if you're watching from Montreal. Of course, we have a 6-meter telescope in front of us to help us do this task, but that explains, I mean, obviously all the instruments are depending on that good view. So in terms of the quick description of the optical assembly, we have an optical ray trace here. I want to point out first with this picture, this is a map of the focal plane of the observatory. So all the instruments share pieces of the focal plane. So the telescope is designed to give a good image quality over this wide an area. And some instruments have better views than others. NearCam, because it has very fine pixels, very small plate scale, it has the best position, rightly so it can give the best images. And so the guider actually requires about 25% of the focal plane, just to make sure that there's always going to be a guide star in the field of view wherever we point the telescope that is suitable, bright enough to actually do the guiding. And when we add nearest to this, we actually gain up to 40. Now we're up to about 40% of the total focal plane. So by any measure, we have a good deal here, both in terms of observing time and real estate in the focal plane. So the guider has has an internal focus mechanism, but it does not have any shutter. We have to avoid at all costs single point failures, which is also why there are two completely independent sets of electronics and imaging detectors, so that either guider, the observatory can function with one guider operational with a slightly reduced performance in terms of guide star availability. But to map the flow through the instrument, there's a fairly large pickoff mirror here. That's what's sitting in the focal plane intercepting these fields of view. And then that is projected onto a 3-mirror telescope here with a fold mirror here. And this fold mirror is actually the focus mechanism, which allows the guider to optimize its focus. Although honestly, the focal range that we can live with the guider is quite large, because we make use of, we don't need the finest image quality to do the centroiding. In fact, it's better if the star is slightly blurred. But we don't necessarily intentionally blur it. We just cover a wide wavelength range, and that gives a PSF that is sufficient for the guiding. So the next chart shows some, just gives you an idea of a couple of the key functions here. So we have the, using a large infrared detector array, we use the same near infrared detector arrays, packaged slightly differently, but the same basic ones as are used in the NearSpec and NearCam instruments. These are the ones actually going from 0.6 to 5 micron in wavelength. And so it does require some sophisticated image processing in the flight software, because infrared detector arrays are not always the greatest quality. It's just the way, it's just difficult to control the quality. So if you're used to a CCD image, these are quite a bit worse in terms of bad pixels. In fact, I'll give you an example here. This is a track image sequence as a movie. It's a false color, so blue is dim background basically, and red is the stars. These are actually all hot pixels. The guide star is actually over here. And the job of the tracking function is to center in the window so that we can then go to find guides. So let's see it, if it does that. And you can see it trying to center this object here. I don't know if you noticed, I hope this is coming through. There is another pixel over here, which is flashing near the guide star. And that is another type of bad pixel that we have to deal with. Some of these pixels are basically kind of like shorts, and they actually cause a problem for the pixels around them, which are actually create almost simulated stars, if you will. So software has to mask all those, including those flickering ones. And you may have also noticed some noise passing through the image, banding noise. So we have all of those things to deal with, and eventually we get to find guide, which is an 8x8 window. And in this case, we took the intensity of the source and ramped it down as we just let the system produce centroids. It was just a measure of the performance versus signal intensity. I should mention this particular testing was done at NASA Goddard with a very fancy optical simulator simulating the whole telescope. So this was the guider by itself operating on these simulated stars. Oops, sorry, I'll go to the next slide if it's behaving. All right, So on to NIRIS. NIRIS basically has a bit of a different path in that it has to produce a good image quality at the pupil that it reimages of the telescope. So we have a pick-off mirror, a 3-mirror telescope assembly, if you will, and then it produces an image of the primary mirror at this point, and then that image is re-imaged well to the focal plane here, and so it has a single 2048 by 2048 infrared detector array. But the important thing is that the light then passes through this dual wheel assembly, which actually has 2 × 9 positions and allows us to put a plethora of different optical elements into the path and therefore produce scientifically useful images in different modes. The focus mirror, the focusing system, I guess, for the NIRIS is a similar focus mechanism construction to the guider, but it's located on the pick-off mirror, which is out front here. And actually this column of baffling here is in front of that, leading to this collimator assembly. And while I'm thinking about it, I'll maybe just show, I don't know if people can see it. This is the scale size of the image at the pupil. Don't know if I can see with my video, but this is, well, you can kind of tell the scale size, about 40-50 millimeters. And that's the image of the primary mirror is produced right here. And this is one of the masks that go in there. So the next slide elaborates on that a bit, just shows you the various optical elements in the pupil wheel and filter wheel. And this is that overall optical layout. And basically, about which combination of these optical elements produces the 4 different modes of the instrument. So we have imaging, we have a wide field slitless spectroscopy where a grism is placed in the path, and we have single object spectroscopy, which is used to basically collect an entire spectrum, 0.6 to 2.5 microns, of a star with a transiting planet, and then tiny bands in this spectrum should show up and should help us characterize the atmosphere of an exoplanet. And then the last mode is this aperture masking interferometry. And if you saw it, that was the mask that I was trying to show on the video. And it can provide a unique view of very close objects to their parent stars, or any sort of close structure around, say, protoplanetary disks, star systems that are forming planets. And so these modes cover the gamut of many of the science cases. I think Jean will talk a bit more about that. I'm going to go on to the build and test of the system. So we had prepared these slides some time ago, and it just showed that the standard processes and testing procedures. Many of you are probably familiar with these things as we build up the boards into their chassis, and the vibration testing and EMC testing and thermal vacuum testing, all of which was done at the David Florida Labs in Ottawa. And for thermal vacuum testing, as I mentioned, the electronics actually sits in a fairly benign environment. It's kept around room temperature. But of course, that's not true for the optical assembly. And this is the buildup of the guider side with the kinematic mounts. We have titanium mounts to mate to the graphite carbon fiber epoxy structure of that the ISOM is made of. And then the actual bench itself is aluminum, and this was machined by LHM in Woodbridge, Ontario. And then we mounted the pick-off mirror and the 3-mirror assembly. 3-mirror assembly was actually, well, the mirrors were fabricated by Corning Net Optics in New Hampshire, because we needed, because of the 0.6 micron operation down to that short wavelength, we really needed a fairly good surface finish. So we needed their LEC process to finish the mirrors. This particular test was the setup where we first made sure the pupil was imaged in the right place, and then place the focus mechanism here for the guider with its turning pickoff mirror, and then the 2 guider detectors are shown here, and this is just an overview after the baffles have gone up. And then On the nearest side, on the other side of the bench, you can see the collimator installed first with the pick-off mirror on the mechanism, and then the detector, the dual filter wheel, and then the wiring and baffles. And then the complete instrument was actually put in first for a pupil alignment test, where we made sure the pupil, the re-imaging of the primary mirror is done correctly. And then after that, it went into the more formal testing, where we presented it with stars. And this was done with our own optical ground support equipment, not quite a full-up optical telescope simulator like they had at NASA, but capable enough for us to verify the performance of the FGS, and that was provided by ABB in Quebec City for us for this project. So, and there it is in the TV3 chamber in DFL, which of course was modified with helium shrouds for this test, because we had to test all the way down to 22 Kelvin at survival temperatures, but operationally between about 35 and 45 Kelvin. And then the completed instrument is shown here at NASA Goddard with some of our team who went down for that. And then just some quick pictures of the FGS located in ISOM. FGS and MIRI were the first two instruments delivered, and actually went through a cryo test together before the other two instruments, a cryo test at NASA Goddard before the other two instruments arrived. And then here's the completed ISOM with all wiring, which is quite an amazing construction with the 4 instruments. And then the next, just that testing continued. They did ISOM vibration testing, and then they actually tested the mirror system at NASA Goddard as well, but they weren't put together and tested together until they went down to Johnson, NASA Johnson, in this large chamber A that was actually used during the Apollo missions, which was completely refurbished and laid out to do optical testing. And this is the main environmental chamber at NASA Goddard. Sorry, I missed that. So, and so, you know, I just wanted to thank the huge team of people that have been involved in this. It is quite an amazing project. We had some great suppliers to produce the FGS NEARES. Here's at the pre-ship review, or the delivery event held at DFL, where just before it went to NASA in July 2012. And but after that, of course, as I mentioned, it's been extensively tested at NASA Goddard and Johnson, and even at Northrop Grumman in Redondo Beach. And then our work continues. So the commissioning team, shown here a couple weeks ago at the Space Telescope Science Institute, you know, consists of CSA personnel, Honeywell, University of Montreal National Research Council, NASA, and Space Telescope Science Institute personnel, who are eventually going to take over the operations once the commissioning is finished. So, so that's it actually. We can stop the share and pass it on to Jean, I believe.
Go ahead,
hello.
Sean.
So can you see me?
Yeah, good.
Yes. All right. So, well, first I'd like to introduce myself, since I think some of you might not know me. So I'm an astrophysicist by training. I've been working at CSA since 2005 as a program slash mission scientist for space astronomy mission. I've been working under David Kendall when he was Director of Space Science at CSA, and more recently working under Gilles Leclerc and Erick Dupuis in the Space Exploration Development Group. Prior to coming to CSA, I've worked several years in the USA from my early postdoctoral years, where I became more interested by space astronomy. It be a great opportunity to work as a postdoc and as a junior research scientist for a few space missions, such as EUV and FUSE, which Canada was a part of. So let me start my presentation. So I'm very happy to talk to you today about a bit more about the science that James Webb will realize. It's so great. I mean, we should be all very proud of being part of this wonderful project, this great endeavor to launch this most ambitious space observatory in space. From a scientific perspective, Webb really represents the beginning of a new era in astronomy, and really is filled with promise to deepen our understanding of the cosmos. I'll go briefly over the four main science objectives of James Webb. But what we shall not forget is thanks to our contribution to this project, specifically of the FGS and the NEAREST that Neil just described, Canadian researchers will have access to this very powerful observatory. Will have access to observation time to take part in these incredible discoveries. So, sorry. So I'll talk a bit briefly about some of the main science team of James Webb. James Webb, as I think was already mentioned by Erick, Dave, and Neil, we'll really observe from, I think, very nearby in our own solar system, in the galaxies, to the confine of the universe. But it will be used very much even to study our own solar system. We might observe some of the planets in our own system, and for example, the moon of Saturn, so for example, Enceladus. But it will also be used to do groundbreaking work on exoplanets. As probably you know, there are over 4,000 confirmed exoplanets, with possibly even thousands of them being in what we call habitable zone of their own stars. And the instrument that we have provided, NEAREST, will be a very powerful tool to study exoplanets by doing spectroscopy of exoplanet. In fact, we'll have one of the optical elements that Neil mentioned is like a very special grism that's optimized to observe exoplanet. And thanks to the observation, we will be able to get a better understanding of their origin, of the atmospheric composition of their atmosphere, and more. So this will be a very powerful machine. And the Canadian astronomers will contribute very much to this aspect of the mission. So as was mentioned, we have, I'll say, in exchange for our contribution, we have guaranteed time observation for the Canadian science team, and about half of the observing time will be dedicated to the study of exoplanets, and that project has a cute name. It's called NEAT, which means nearest exploration of the atmospheric diversity of transiting exoplanets. but nearest will also be used to study like the brown dwarfs, which are sort of the fail stars, rogue planets, protoplanetary disk. You can name it. So yeah. I'm having trouble with it. Okay. Then another major science theme of James Webb will be the study of stellar life cycle. So thanks to all these, we have nearest, but there are like 3 other instruments on James Webb optimized for infrared observation, from the, let's say, the near infrared to the mid infrared. So these instruments would be very powerful to probe the regions where stars are forming. Basically, infrared, these regions are dense, relatively dense. They have dust which absorb optical light, and by observing in the infrared, we're able to like peer in those clouds, and we'll really learn very detailed information about how stars are forming, or like baby stars interact with their environment. We'll learn how stars, I would say, end their life, and exactly how. For example, the picture here shows an example, like in the sorry, in the bottom left, you see a nebula that's like a star that just like shed its outer envelope. And so James Webb will be very powerful to probe I would say, the environment of these stars and really learn detailed physical information about these gases, how rapidly they expand, their temperature, and so on. And again, the Canadian astronomers will already have approved program to study these type of we'll say, of studies. We have like an early release science project that is led by a professor at Els Peters from the University of Western Ontario, that will like study how hot stars really interact with their surrounding. We'll have guaranteed time observation to study protoplanetary disks, disks in which planets form in the galaxy, and with there are a few geo programs to learn probably what are the most incredible explosions of stars, like collisions of neutron stars called kilonova. You probably heard about an event that was detected a couple of years ago by a gravitational wave event. So this team will be on the lookout for the next event, and will use James Webb to observe the results of this merger. And their proposal to observe brown dwarfs, white dwarfs, which, by the way, are maybe my favorite objects, is what I do research on. So it's very fascinating to all the range of application that James Webb will have. James Webb, I will say, was probably more conceived with the intention of maybe studying more the early universe. So, as Erick said, James Webb will be a basically a time traveling machine. We should be able to detect light from the first galaxies, the first generation of galaxies, maybe the first stars, which were formed a few 100 million years after the Big Bang. This first source of light, when they appeared, they end what we call the Dark Ages. these first stars were much more massive than, we'll say, like the sun or the stars that we would typically know in the galaxy. And to produce, I believe, to produce intense UV radiation that reionize the neutral hydrogen in the early universe to start what we call the epoch of reionization. And there are still a lot of like questions about that epoch. The current instrument, I think we're able to answer some of them. With James Webb, we should get a much better understanding of what happened in this early phase of the evolution of the universe. So these first generations of stars were, thought to evolve extremely rapidly and explode as probably supernova, and astronomers believe that these are the seeds of like supermassive black holes that are observed at the centers of nearly all massive galaxies. So we should get a lot of insight on how, I guess, the universe started and all the first galaxies formed, and where the black hole coming from. James Webb also will be, as I said, an extremely powerful time machine that will allow us to take like snapshot of the universe as at various age, and it will help us understand how galaxy evolve over time. There's still a lot of mystery about how galaxies are forming, or they evolve, or how they interact with each other. As you know, we have probably all seen pictures of galaxies and it's quite amazing to see the diversity of shape the galaxies have, of size. You have like spiral galaxies, elliptical, irregulars, and so with James Webb, we should hopefully get a better understanding how they came to have these shapes, how did they evolve. So we should get more insight about that. And galaxies are important as well because that's where stars form. So we should gain also a much better understanding of star formation as a function of the age of the galaxy, and those stars generate heavy elements that we're made of. And again, Canadian astronomers will contribute to this effort. There's another GTO program called Canucks, another funny name, that will be dedicated to, study galaxy evolution, but also the first theme. It will use like a massive clusters of galaxies that acts as a gravitational lens. That allow us to even peer farther away. So she'll be able to see very distant galaxy thanks to this very special effect that nature is providing us with. So in summary, Webb is the most complex and powerful space telescope ever built. So we're lucky to be part of it. I'm very excited about the launch, which is supposed to happen on December 18. This has been done in collaboration with NASA and ESA. We're an official partner of this super ambitious mission, so that's a big deal for Canada from a Canadian perspective. And our contribution to the mission will really give access to this fantastic facility to the Canadian astronomical community to study and further our understanding of the universe. And and that's thanks to the contribution of as explained by Neil of this fantastic team that work on the development of James Webb. I mean, it's a huge team if you include like the people in the US and Europe. It's probably thousands of people. It's probably more, about 100 people in Canada. So it's been a wonderful collaboration between industry, government, and the academic community. So it's quite an adventure we've been part of, and it's only beginning after we launched in December 18, and we looking forward to see the first image from James Webb. So that's it. Thank you.
Okay, thank you very much, Jean. That's great, and thank you all four of you for this overview. This is really fascinating to see this. I'd like to invite all of you to put your camera back on, and we'll stress the system. So far, hopefully everything stays working.
This is Todd from Cassie. I am on it if it fails. Let's give it a try.
Well, we have been good for 45 minutes, so that's awesome. So I have a couple of questions for these four fine gentlemen, but you know the prize for the best question. Please put your questions on the bottom right in the chat, and I'm keen to see who has the most interesting question. Just to kick it off, on what you finished your presentation with, Jean, is so this is a massive multi-decadal international collaboration of multiple countries, continents, companies, space agencies, each with their own cultures, technically, programmatically, politically. For any four of you, is there an aspect about international collaboration that you discovered during this program and that you didn't know beforehand? Anyone?
Well, maybe I can start. I'll go a little bit beyond the James Webb example, Daniel, if you don't mind.
Oh, absolutely.
And actually, this is a talk I gave to the U.S. National Science Academies a couple of years ago. And it's a lesson for Canada in general. We are a very ambitious space nation at times. We've been on amazing missions in the past, in the present, and will be again in the future. By our very nature, I would say most of the time we are bound to operate by international collaborations. We tend not to do full end-to-end missions on our own, but rather to team up with some important partners and provide critical infrastructure, just like we're doing on Webb, and reap amazing benefits in return. Now, the challenge with that, and that was the conclusion of my message at the time in Washington, was sometimes we feel like a mouse that's sleeping in bed with an elephant. What is an extremely big deal for us can seem like something which is trivial for our partners that have much higher stakes in terms of financial stakes than us. But small decisions on their side can have major impacts and repercussions on our side. And we've seen that through past missions where decisions were made that ended up throwing us massive, like really important curveballs, or even resulting in cancellations of our missions. So maybe what I can say for Webb is it's even worse when the elephant is actually not just turning in its bed, but it's tossing and turning and having nightmares, just like the few times when Webb almost got canceled in the US. And maybe Dave can probably tell that story better than I can, and just segue from here into what did happen to Webb a few times in the US that gave us shivers in Canada.
Yeah, thank you, Eric. And you described the situation, international situation, very well. The thing I would like to add to that initial question is that over my long career, I've been involved in a lot of different collaborations, international collaboration, being very fortunate. And then in the last part of my career, I was the chairperson of the United Nations Committee on the Peaceful Uses of Outer Space, where you're trying to deal with 90 different space states and trying to get consensus. And it's a very interesting challenge. But going back to our sort of contributions, Canadian contributions to various space missions, my view is that this really does stretch our capabilities. It stretches our scientists. It stretches the agency that is managing the projects. It provides new insights, and it stretches industry. And this is really, I think, what's so important about these international collaborations. And James Webb is one. We've mentioned Fuse as another. And as Eric knows very well, as we go more and more into the Artemis program with the United States and its partners, it's going to stretch us, and of course the International Space Station. Each of the states you're dealing with really does have, if you boil it down, have different cultures, have different ways of working, have different approaches to solving problems, and you just need to learn that. You need to appreciate it, and it provides often just a wonderful insight to everybody as to how you do come out the other side. And all these projects, we've been very successful at coming out the other side. Canada's done, I'm guessing, close to 200 international collaborative projects. A lot of them on the International Space Station, of course, over the past 40 years. And most people don't know the depth to which Canada does collaborate internationally, and it's very impressive. And these have stretched our people and made them better, and have made us a very much stronger partner and a very much stronger, I think, team as we develop these various collaborations. I will segue into what Eric, since I have the mic, into what Eric said and near-death experience of James Webb. Certainly, there are several examples of that. Canada is not immune to the fact that we had to go back to Treasury Board probably too many times to convince them that this was something which we should still be involved in, which is not an easy business in our country. But in the United States, in 2011, it came to a very close near-death experience in that it was already 3/4 of the way basically through the project. $3 billion had been spent on it. And yet the House of Representatives, the Appropriations Committee, that is called the Commerce, Justice and Science Committee, which controls the budgets of NASA. And it moved in 2011 to cancel the James Webb project for the fiscal year 2012. And if that had happened, they basically suggested to remove $1.9 billion from the NASA budget, and just to say, okay, that's it, that's finished. And the budget. So this was a very, very difficult thing to do, because normally the House of Representatives listens to its committees, especially its appropriations committees, and you have to be brave to go against it. And to cut a long story short, this was effectively nullified in the end by one senator, senator from Maryland called Barbara Mikulski, who basically went to fight for James Webb very aggressively, very effectively. And thanks to Senator
Milkowski, who is now retired, it was saved. But we were just we and the European Space Agency were just standing there saying, we couldn't do anything. This was an internal U.S. issue, and fortunately it survived and has gone on to be it will be the great success we expect. And but yes, these things happen. They happen, unfortunately, a little bit too frequently, and you have very sleepless nights about them.
And Neil, were there any technical near-death experiences where we had to change the laws of physics?
Well, of course, we had the Eidolon issues, and we felt we would eventually overcome them with enough time, but we were really running out of time. I mean, it was impossible to fit it in. I mean, we had talked even about actually replacing some of the components while it was down at Goddard, and that was after delivery, but that was not viewed favorably. But surprisingly, in the end, we ended up doing just that, because I don't know if people are probably aware of the detector degradation that all the near-infrared instruments suffered. There was an issue at Teledyne with a slight process change was made to produce the original JWST arrays, and it turned out to be a problematic one. So all the instruments had to deal with a detector replacement program, which we successfully did. All credit to my colleagues who had to do the very delicate operation of replacing the detectors while down in the Goddard clean room. So yeah, there were a couple of scary moments for sure.
All right. So we got our first question. Great. So this is from Romain. What do you think is the most critical step during the deployment of the telescope in space? What are the plans if something is not working properly, as a repair might not be possible like it was with Hubble? Who wants to take that tricky topic?
I can start, and then somebody can pick the ball from me afterwards.
Okay.
So thank you for the question, Romain. First thing that I have to say is it has to work. It's that simple. And that's the reason why the mission has been delayed so many times. Or it's part of the reasons why it's been delayed so many times is they cannot afford to fail. First of all, it's $10 billion US. It's going to be at a Lagrange point, which is very far from Earth. So it's not like Hubble in low Earth orbit where you can just send the space shuttle and fix it, put a new set of reading glasses on it and have it fixed. If it doesn't work, it's going to be a catastrophe. So they are extremely rigorous about making sure that everything works. Now, I'm not sure if you've seen this video from NASA with the Mars landings. They had, I believe it was the 7 minutes of terror. Now they have 29 days on the edge because it's going to take 29 days for this thing to unfurl. They have to unfold the mirrors, and then they have this huge heat shield, the solar shield composed of multi-layer insulation that has to unfold and then unpack. And if that doesn't work, there's very little that can be done. So they would have to basically do operational fixes. So unlike Hubble, this one will not be fixable. It really has to work on the first time. And I don't know if anybody else wants to pick up from here.
I'll just mention, Eric, that I was reading a little bit of course, background to the James Webb, and they had a review in March 2018, which I'm sure you and Neil are very familiar with, and Jean. And the review found that this project has 344 single-point failures, each of which cannot fail. You talk about being on the edge. This project really is quite remarkable. So it's going to be as you say, a lot of fingernails are going to be bitten down in those 29 days.
Yeah, I should mention that most of the single point failures are mechanisms, of course, and most are actually redundant in terms of the wiring, but there's always that point at which you just cannot make redundant, or the system just becomes completely unwieldy. So yeah, it's pretty scary. I think the scariest one is the secondary mirror deployment, because if the sun shield doesn't completely deploy or not all the layers separate, they talk in terms of degraded performance. If even one of the mirror segments seizes, we can have slightly degraded optical performance, but still do useful things. But if the secondary mirror doesn't get out in front of the primary mirror, there's no light passing through to the instrument. So it's a pretty scary one there.
So Jean, at what point in time would you sigh a breath of relief?
Sorry, I
When would
misunderstood.
you feel relief, or what point in these 29 days is there?
Probably at day 30.
Day 30.
Yes.
Yeah. All right, we got another question from Jeff. How long will unpacking and testing take? When is the first image expected? And has it been decided what the first image is going to be from which celestial body? Anybody know?
Yeah, about the first image, there is like a committee looking at that. It will be called the early release observation (EROS), and it's kept secret, so we don't know yet. They've kept that secret. Yeah.
Wow.
So it will be a surprise.
So,
And to answer,
yeah, the unpacking. So go ahead, Eric. Yeah.
I was just going to say, and to answer the first part of the question, well, there's those 29 days of living on the edge to unpack, but it's going to be followed by at least 6 months of commissioning. 6 months is the planned commissioning period, and if anything is more complicated, it's going to take more time. So you can expect that after Webb gets to its Lagrange point location, it's going to take another 6 months of commissioning before it's fully operational for science observations. Now, having said that, there will be imaging during that commissioning period, but it will be fully operational only 6 months later at the minimum.
So I have to say, from an engineering point of view, I guess the very first images are going to be of a pretty bright but completely nondescript star that they're going to be using to tune up the telescope. So those images will be pretty rough to begin with, but that's the whole point. They'll be using it to tune in and narrow down. And in fact, that whole process can go through. I mean, they're only planning on one iteration, but there's contingency plans to go through it 2 or 3 times if they have to. Because you can imagine getting all 18 segments tuned up and balanced is a complicated problem with possibly many minima. So they need to do it carefully.
Yeah, I would say that even the guider will be used during that phase, during what they call this telescope alignment, OTE alignment, or so our guider will already play an important role.
All right, we got another question. And you haven't launched yet, but here's all. Patrice is asking, what's the next generation telescope or observatory, I should say? Any thoughts already? What is next? What's coming after this?
I think an astronomer has to answer that one, because NASA just published their decadal plan last week or the week before. So they know where they're going, and Jean is probably the best person to answer that.
Yeah, well, you're right. So that people have been thinking about that for a number of years already. Like looking to, okay, what will come next after James Webb, because these projects, you see James Webb, it took about probably over 3 decades to get where we are. So we have to start thinking right now. So yeah, so people have been thinking of probably a super James Webb, like how I think there are a couple of concepts that have been mission concepts that have been considered, such as Louvoir or ABEX. They are looking at an X-ray mission. There is a mission called Origin that would be more dedicated to the far infrared. So far, they have not selected which mission it will be, but they will, I think, keep on developing technology that might be relevant to that next flagship mission. And these projects will certainly be international partnership. I think there's no other way of doing it. So James Webb was, I would say, an excellent way of learning how to do these super ambitious project. Like Louvoir, I think they are considering like even a 10-meter telescope, which is wow. Okay. Probably segmented, and it will use with the next generation of large rockets. Although I think what's being now considered in the decadal survey is more a compromise between Louvoir and ABEX. I think it's a 6-meter or 7-meter. Maybe Neil, you know. So there are lots of ideas around the. So people are really forward-looking in that field.
And Neil and David, you want to comment on that?
Well, I mean,
I think that one of the expectations of James Webb, of course, is the whole question of, are we going to find exoplanets that have potential for life, or even, you know, signatures that oxygen, methane, and signatures that might be indicative of something happening there. This is of course the big thing that everybody is going to be very excited about. It will need other more sophisticated instruments, even beyond James Webb, I think, to really look at these objects. And I am optimistic that we're going to find exoplanets with the signatures of gases that really are curious to us and indicate that there's something going on there. And there would be a huge, I think, outwelling of expectation to put together something massive, as John says, that will then really give us hopefully much more information. It's just the thing that really has caught, I think, the public imagination. So the other panelists might disagree with me, but I think that's going to be a real focus as we move forward.
Yeah, well, I can confirm that my 11-year-old asked exactly that question. How many other Earths are there? And how would we know? So we're probably where we were 30 years ago before the launch of Hubble. And we're going to see all kinds of discoveries that we haven't even thought about. I've got another question here. What is the life expectancy of the telescope on paper? Do you think it will pass Hubble, what has achieved? And after so much waiting, and could complexity bring the expected failure rate to an earlier date? Well, that's a little... You don't have to answer the last part. But... You really want to take that one?
Well, it's a fair question. I think even the last part, so the official on paper life expectancy, I mean, the design requirement was for 5 years post-commissioning, so 5.5 years. And of course, we have to add, in some cases, other required factors on that for the various systems. So generally, everything's designed for 10-year life. I mean, putting aside any reliability and failure rates, the main limitation there was the onboard fuel, which is required, after you're reorienting the spacecraft so much you have to dump momentum, and that means that you're eventually going to run out of fuel. So obviously they look at that and try to minimize that in operations. But in terms of reliability, all major subsystems are fully redundant. So we can have failures in the guider, like I mentioned, or in NIRCam, and still have significant capability.
Okay. I don't see any additional questions. Then I have one last question for you guys. Is other than other habitable planets, what other discoveries would you like to see? What are you hoping for? What are your dreams with this observatory? Anybody?
I can start if you want.
Yeah, go ahead.
I'll just pick up on what I said before. I think that there is a lot of public interest, as I said, and I think curiosity, including I think in the team and in myself, as to whether or not we can pick up a signature of a gas in a planet which is in what is commonly called the Goldilocks zone, where it's not too hot and not too cold, and that we believe that that life could have evolved or has evolved. I know it's just a big outstanding question right now, and we'll obviously be plowing more into looking at some of these moons in the solar system. That then there's a lot of interest in that. But that has to be a defining point if there is some evidence of an oxygen or methane or other atmospheres that we know from our own experience have been created by life forms. And so that's going to be, I think, a very compelling thing that is going to be in the minds of a lot of people, and including the people who fund it. I mean, in the end, astronomers and scientists are reliant on the public to fund this. There has to be, the $50 million, the $200 million actually, which Canada has put into this project is funded by the taxpayers, and I think we must not forget that. And the taxpayers are fascinated by astronomy and they're fascinated by this question of life, I think, and the same thing in the United States and in Europe for the other two partners. So I'll leave that to others to maybe make their own wish.
So Neil, Jean, you want to add to that?
Sure. I mean, I have a soft spot for the nearest and the single optic spectroscopy mode that will hopefully detect the gases around an exoplanet. But I have to say, when you look at the sensitivity increase from the mid-infrared camera on JWST is going to provide basically an increment of 10,000 in terms of sensitivity over anything that's been fielded before, including the Spitzer Space Telescope. So I worked on the testing infrared arrays for Spitzer, put me through grad school. So soft spot for mid-infrared. Anyway, I would really like to see the first images of the center of our galaxy using the MIRI instrument, because they're going to show detail that we never dreamed of. So I'm anxious to see that.
Yeah, personally, I like spectroscopy. This is what I used to do a lot especially in the UV or in the extreme UV. So I really look forward to see what we'll learn. I mean, what we didn't plan on learning, what kind of surprise we'll have with James Webb. What will we have to revise some of our theories? I really look forward to see the spectra from the most distant object that we'll be able to detect with James Webb, but what we'll learn from them. I'm just very impatient to see these first image, but spectra as well, because like James Webb will be a fantastic spectroscopy machine.
All right.
And maybe if I can compliment Daniel, first I'll say congratulations on your question. Sarah Gallagher got the very same question from a journalist earlier today. And her answer was, this is like asking a parent who's their favorite child. There is no right answer to that question. However, as the oddball on this committee, I'm not a scientist, I'm not an astronomer, I'm an engineer. And I will go back to what David has said. For the general public, if we were to ever find either biomarkers or signs of a habitable planet in the sweet spot around another star, this is a civilization scale discovery. This would basically it would throw many of our beliefs upside down, right? I mean, our civilizations, and this goes beyond science, right? It's philosophical, it's religious. I mean, you name it. Finding life elsewhere in the universe would be the single most fundamental discovery anyone can ever make, in my opinion, or at least in the public's eye view, with the James Webb Space Telescope.
Mhm.
I think that's a perfect finish to our panel here, Eric. I'd like to thank all four of you for participating on this panel and your contributions. I really enjoyed it. Thank you so much. Thank you for all the questions from the audience. I think Jeff is going to come back on to close out the session, but I really want to thank you. It was a lot of fun doing this. Eric?
I have a question for you, Dan. You made a promise at the beginning of this panel, and I want to know who's going to win the beer, and I hope it's not Jeff, because that would look fixed.
So I'm going to disqualify Jeff because he's from he's an organizer, so he doesn't count. And I would very much enjoy to invite Romain, Patrice, and Dagan, all three of you, to come at our next in-person Astro to have a drink of your choice with me and the panel, if you can join as well, to celebrate a successful launch of
And the technical staff.
well, there you go.
Yes.
And Cassie will buy.
Oh, there you go. I love giving out prizes like that. So thank you so much, and thank you for having me, allowing me to moderate. It has been truly a joy. Thanks.
Thank you, Daniel, and thanks to our panelists. It's it's not every day. It's not every day that a group of such éminence grise are brought together to talk about something as momentous as James Webb undoubtedly will prove to be. Should it discover life elsewhere in the universe, that would be incredible. But the discoveries that are perhaps more predictable that Webb will make themselves are almost unimaginable, and just stretch our knowledge to the breaking point. It's just amazing. And we appreciate, by the way, not by the way, but especially the support of Airbus and Daniel, representing Airbus today, for the support that they've given to Astro. I really hope that we can reconvene in person next spring or summer. We will be polling the participants in Astro this year to find out if, let's say, a 6-month delay is too quick between now and the next Astro conference, assuming it's in person. We need to get some feedback from our participants about that, so we will be doing that. The program tomorrow, for those numerous people who are still connected with us, it kicks off with another very distinguished guest, and we're delighted to be able to have Jenny Seide Gibbons, who is one of the Canadian Space Agency's newest astronauts. She'll be talking about a suborbital research opportunity, soliciting interest from the space sector. She's going to want to solicit your interest. This is intended to be very much an interactive session. because Jenny is as interested in finding out what the Canadian public, the Canadian science public, would like to do with this prospective mission, as I'm sure everyone else is, to ask Jenny questions about, you know, how do you get to be an astronaut? What's life like? What about the travel? Blah, blah, blah. The other plenary event immediately following Jenny's is test beds and analogs. And this, I think, will be an interesting discussion between our two conference technical co-chairs, Phil Ferguson and Mick Faragalli, and three folks who are very much involved in test beds, to describe what their facilities are like, what they're intended to do, and to share information about that. It's not everybody has a decent test bed or has put together an analog environment. And so I think this should be very interesting for everybody to participate. And then we have the technical sessions to conclude that day, 3 of them. On Friday, just to touch on that quickly, Defence Research and Development Canada is holding a workshop that will last the afternoon. It's chaired by Dr. Lockie Scott, who is a DRDC research scientist, and there will be several experts in the area of space domain awareness. You can see in the program, actually, if you go on the website, if you like a PDF document, you'll see on that document the lineup of the participants, or within FeedLoop. The result of this workshop, there will be 2 parallel discussion groups. They will reconvene, share their results, and there will be a summary of their key findings. So this, I think, is it's a reprise of a previous event that Cassie facilitated for DRDC. I think they find it valuable that we provide an opportunity for their community to come together, and I hope some of us will have the opportunity to participate in that. So finally, thanks again to all of you for such a wonderful experience and rare opportunity. I can't hold my breath for a month, but it'll come pretty close to that. I guess it's the 18th of December, if I'm not mistaken, and hopefully the launch will not be postponed, and the 29 days of White Knuckles will begin. Anyway, thanks again, everyone. Have a good evening, and take care.
Okay, thank you.
Goodbye. Thank you.